So good evening, everybody. So I welcome to our today's resource person, Dr. Atul Bhat sir, and I welcome to our Academy CEO, Dr. Ramesh sir, and Academy President, Professor Ayappan sir, and I also welcome all the attendees and lecturers and teachers. So I have give small introduction about Dr. Atul Bhat sir, noted MSc in Physics from Jain University, has been teaching physics since 2016 and working at PPC since 2019. Also working as a coordinator of Purna Prajna Amateur Astronomers Club, working on popularizing astronomy among public through PAAC. And has been invited as a resource person for several Skywatch programs, talks on astronomy and physics, has been published in a peer-reviewed journal and has presented at national and international conferences. Gave talks on rotational mechanics in the webinar series twice for KSTA, this being the third one. So thank you. Over to you, sir.
Okay. Good evening, everyone. Today we will be exploring a very important topic in physics, that is gravity. All of us know that gravity is something that has been there and we know it from a very young age. Gravity ಅಂತಂದ್ರೆ ಗುರುತ್ವಾಕರ್ಷಣ ಶಕ್ತಿ ಅಂತ ಹೇಳ್ತೀವಿ. So that is something that pulls us down. ನಾನೇನಾದ್ರು ಹಾರ್ತೀನಿ ಅಂತಂದ್ರೆ ನಾನು ಕೆಳಗೆ ಬೀಳೋದು ಗ್ರಾವಿಟಿಯಿಂದಾಗಿ. ನನ್ನ ಕೈಯಿಂದ ಏನಾದ್ರು ತಪ್ಪಿದ್ರೆ if it falls down, it is because of gravity. So let us understand what exactly is gravity. Before we start understanding exactly what is gravity, let's learn a little bit about what was known to us about gravity before what is known to us today. So long ago, in the Greek civilization, Aristotle, the teacher of Alexander the Great, observed that heavier objects fall faster to the ground. So he said object fell towards the earth, which is the center of the universe, is what they believed, and the earth attracts all the mass in the universe towards it. And he also said that heavier object falls faster and lighter objects fall slower. So if you drop a brick or a 1 kg rock and you drop a feather, then of course we all know this, the brick will fall faster. So Aristotle said anything that is heavier in mass will fall faster towards the ground compared to anything lighter. In ancient India as well, Aryabhatta said that something that holds the celestial body together, otherwise they would be pushed away by the centrifugal force, that is gravity. So he's mentioned about a force. He did not name it gravity, of course. He mentioned about a force where he said that it is holding all the celestial bodies together. Otherwise, because the earth is going around the sun, or all these comets or even the moon going around the earth, they would be pushed away because of the centrifugal force. So Aryabhatta also mentioned about this force, and Brahmagupta, oh, the font is not supported here, but Brahmagupta was the first one to coin the word Gurutwakarshanam, which is Gurutwakarshana Shakti, that is gravity. So in the medieval philosophy, that is medieval times, what they observed was Galileo was the first one to play with this gravity. So what Galileo observed is when he dropped two objects from a plane, uh, these objects usually roll down together. These were solids and he made it a cylinder so that they can roll, but irrespective of their weight, they always roll down together. So he tried changing this with the size of the objects. So now he's changing with the mass of the objects. So you can see in the second image, the red cylinder is bigger. So obviously it's quite natural to assume that it has greater mass. And the lighter white cylinder is also rolling together on this inclined slope. Galileo also tried this with hollow cylinders just to adjust their masses and sizes. Yet they always roll down together. So irrespective of the size, irrespective of the mass, irrespective of hollow or full, these objects always roll down together. And this was something very peculiar. So this is a better demonstration of a cube like ice without friction, a solid sphere that is depicted in yellow, a cylindrical shell which is hollow, a solid sphere, and a spherical ball. So you can see they roll down at different rates, right? So it was not that everything fell down together, but depending upon their shape, depending upon the material used, depending upon their geometry, things would roll down at different rates. But two objects of the same geometry would always roll down together. So until Galileo, the world believed that if you drop two objects, a heavier object would fall down faster and a lighter object would fall down slower. So you can see here that there is a heavier object, bigger object over here, and we'll assume that it's of the same material, a smaller object. So naturally, lighter object would fall slower. But what Galileo observed is that when he dropped these objects, today it's a popular uh, story that Galileo went to the Leaning Tower of Pisa and dropped them. We don't know if it really happened or not. But when Galileo dropped these objects from a different height, ಅವನೇನು observe ಮಾಡ್ದ, both the objects, irrespective of the mass, fell down at the same rate. So this is something new that the world was not knowing. Galileo told us that two objects of the same material, irrespective of their mass, if their geometry is the same, they fall down together. And this was also repeated when we went to space. The astronauts on Apollo 11 dropped two objects. One was a feather and one was a hammer. And you can see in this image, not very clear, I'll show another image later, that both the objects dropped at the same time. So it was true what Galileo observed, and we did not have an explanation why. Because until then, the only physical or the scientific explanation was given by Aristotle. He had explained it beautifully how heavier objects fall faster, but now Aristotle was probably wrong. Kepler's laws were a instrumental study during this time, where Kepler said that objects move around another object in elliptical path. So this was also important because planets were going around the sun, and for some reason they were held together by some unnatural force. This is an inspiration that led on to the next study about gravitation, which is the Newton's law. We all know that the apple story, that when Newton was sitting under a tree, an apple fell on his head, and that led him to question nature. Why does the apple fall down? And when he questioned, he realized that the apple falling down was similar to that of the earth going around the sun and the moon going around the earth. He was relating the fallen apple to the wonders of the cosmos and the celestial movements. And that is when Newton realized that every particle attracts every other particle in this universe with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Or to put it in equational form, this force that is acting on everything is directly proportional to the mass of the first object. It is also proportional to the mass of the second object, and it is inversely proportional to the square of the distance between these two objects. This is the inverse square law, where Newton related the force being relational to three particular parameters between these two objects. And that is when he related these three relations into an equation where he said force is directly proportional to the force of the product of the masses and inversely proportional to the square of the distance between them. And when you add a proportionality constant, we get F is equal to gmm by r squared. This is the famous Newton's law of gravitation, Newton's equation that explains gravity. The g there is known as the universal gravitational constant, and its value is 6.674 into 10 power minus 11. I have not written the units there so that the viewers can figure it out themselves. It's easy, it's cross multiplication. You take r square, m and the small m to the other side along with the force. Force is Newton, r square is meter squared, and then two masses sum up to kg squared. So you can easily calculate the unit of g. Okay, so value of g is 6.67408 into 10 power minus 11, and this is a universal constant, so it must be same across the universe. So when we learn gravity, we also need the other law of Newton, that is the rate of change of momentum is directly proportional to the force acting on it and takes place in the same direction as the acting force. If you know this law, then you know that this is the Newton's second law, which says that the rate of change of momentum dp by dt is directly proportional to force, or if I expand the momentum term there, I get m into dv by dt. because mass is a constant for any given object, is directly proportional to force. And if I can write the proportionality constant, I get a k, and dv by dt becomes a. So I get F is equal to kma. But because we define the force, k can be taken as 1, and we therefore say that 1 Newton is when mass and acceleration are equal to 1, or the product of them leads to 1. So we have the famous equation F is equal to ma. So now we have got two equations. So let's relate this to all objects. An object falling towards the earth is pulled down with the force of gravity, that is F is equal to gmm by r squared. And on the same object, when gravity acts with this force F, it falls down with an acceleration a. But hereafter, for all falling down objects, we take the acceleration as g, just to differentiate between horizontal acceleration and falling down because of gravity acceleration. So we have two equations for force now. F is equal to gmm by r squared and F is equal to mg. Both are the same forces. It's the gravitational force acting on it. The first equation tells me how the force is because of the mass of the earth and the distance between the object and the earth. And the second equation tells me that if this gravitational force is acting on it, then the acceleration experienced by the object is equal to this g. So if I equate these two equations, then I'll get gm is equal to capital G capital M into m by r squared. We have the same mass of the object on both sides. I will cancel them and I'll get G is equal to, or small g is equal to gm by r squared. Now, G, capital G, is the gravitational constant. M is the mass of the earth. So r is basically the distance between the object falling and the center of the earth. So for an object falling on the surface of the earth, this r can be easily the radius of the earth. So I'll substitute the radius of the earth and the mass of the earth. And when I put in these values, gm by r square becomes 6.674 into 10 power minus 11 into 5.972 into 10 power 24 divided by 6,371 into 10 power 3 whole squared. Okay, because the radius of the earth is 6,371 kilometers. The 10 power 3 comes from the kilo. And you can imagine the size of the earth, the mass of the earth is 5.9 into 10 power 24 kgs. So when I substitute these values, I will get G is equal to 9.81 meter per second square. You see, the units are the same as acceleration. This is because any object that is dropped on the earth falls down with an acceleration of 9.81 meters per second square. That symbol there, a plus inside an circle, is nothing but the symbol for earth. So whenever I put the symbol, you know I'm talking about the property of the earth. So on earth, G, acceleration due to gravity, is 9.81 meter per second square. What would be that on Mars? On Mars, I can get this value if I substitute the mass of Mars and the radius of Mars. Let's do that later. So first, before I move further, I need to differentiate between weight and mass. Mass is a property of any object. When I say I'm 62 kgs, it's not my weight, it is my mass. And the weight is the force acting upon this mass of mine, that is 62 kgs, with an acceleration of 9.8 meter per second square. So an object falling towards the earth falls with an acceleration of 9.8 meter per second square. So the gravitational force acting on this object would be its weight. Please understand, we today, because we have mistook these terms to say my weight is 62 kgs. No, the weighing machine is actually measuring in newtons, and it is telling me that if your weight is somewhere around 670 newtons, then your mass is 62 kgs, or 610 newtons, then your mass is 62 kgs. So the machines are calibrated to tell me my mass, not my weight. It is measuring my weight. So an object weighing 40 kgs, again, when I'm saying weighing, I'm telling its mass over there. So an object weighing 40 kgs, or an object of mass 40 kgs, is equal or is acted upon by a force of gravity leading to a downward weight of 392.4 Newton. That is 40 times G, which is 9.8. Similarly, an object weighing 40 kgs, that is the mass of an object being 40 kgs, if I take it to Mars, then when I multiply it with the G of Mars, I will get it as 142.1 Newton. So what is actually the G of Mars? You can say that it's less than that of Earth because of the numbers there. On Earth, the weight is 392. On Mars, it's 142. So of course, G on Mars is lesser. Let's find out how. Okay, it's roughly around 3.72, but let's find out how. What I have here is a table which tells me the relative mass and the relative radius of these objects. I've not written the actual mass. So here I'm trying to tell you that if the mass of the Earth is 1, at 5.2 into 10 power 24 is 1, then Venus's mass is 0.815 into 5 into 10 power 24 kgs. Or for Mars, the mass is 0.107 into Earth's mass. Okay, so it's a relative mass. Similarly, relative radius. This helps me in the calculation. So now a 1 kg stone on Earth will weigh 9.8 newtons, 1 into 9.8. So 9.8 Newton is the weight of an object, 1 kg is the mass of the object. And let's calculate the same for Mars. On Mars, we have got G is equal to Gm by R squared. I will put G as 6.674 into 10 power minus 11. The mass for Mars, I'm substituting as 0.107 times 5.97 into 10 power 24. Please understand, this is the mass of the Earth, and I'm just getting 0.107 times Earth's mass. Similarly, Earth's radius times this relative radius of Mars, that is 0.533. So when I do this calculation, I'll get that G for Mars is 3.78 meters per second squared. So a 1 kg stone on Mars will weigh 1 kg in mass, but 3.78 newtons. So its mass does not change, but its weight will change on Mars. Similarly, on Jupiter, if you do this calculation, you'll get its weight of 1 kg to be 24.84 Newton, right? So this, oh, sorry, 24.84 into meter per second squared. So this is, yeah, okay, sorry, I've made a mistake over here. This is G on Mars, so 3.78. So similarly, this is G on Jupiter. So 1 kg on Jupiter multiplied by this number will give me 24.84 Newton. That means G on Jupiter is 24.84. If I drop an object of 1 kg or any object of any mass on Jupiter, then its acceleration downwards will be 24.84 meters per second squared. So a 1 kg object will weigh 24.84 Newton on Jupiter. Now let's talk about free fall. Free fall is when you fall freely under the effect of gravity. Nothing is holding you back. You're simply falling freely. You know, we have all seen skydiving videos, and they, after a while, they attain this kind of a steady state. And you need to understand that anybody falling freely under the influence of gravity on Earth will fall with an acceleration of 9.8 meter per second square. Wherever they are on sky, they are on the ground, wherever they are for small distances from the surface, that is our airplane distance, not in space, it is 9.8 meter per second square. So an object falling down will fall with an acceleration of g, that is 9.8. And from Newton's equation, I can deduce, this equation is there. We all know the equation of motion. V squared minus u squared is equal to 2as. So when I calculate the values, any object when it begins to fall, its initial velocity is 0. So u is equal to 0. I'll get v square is equal to 2gs, or v is equal to square root of 2gs. I know g is equal to gm by r squared. So I'll substitute the same. Okay. And I know v is equal to displacement by time. So I'll substitute the same. So when I substitute that, I will get s by t squared, because okay, yeah. So s squared by t squared is equal to 2gs. I will simply cancel one s on one side and s on this side. So s squared cancel with an s over here, leaves me s by t squared is equal to 2g. And similarly, when I just cross multiply stuff, I'll get t squared is equal to s by 2g, or t is equal to square root of s by 2g. Now notice something, g is a property for the Earth, so it's 9.8 fixed on the Earth, and s is the distance from which the object is fallen. Mass is not there in this equation that tells me the time of flight. So an object falling down, irrespective of its mass, will fall down in the same time. Therefore, two objects falling from the same height will fall together. On Earth, they've done this demonstration, but on Earth, because we have air, to drop a feather, I need air resistance to be removed. Therefore, inside a vacuum, they did this experiment where they dropped a bowling ball from a height along with feathers, and you see, when both are dropped together, they fall down in the same time. Therefore, Aristotle was wrong and Galileo was right. Two objects falling down will fall at the same rate and fall down together, irrespective of their masses. Now, for a simple pendulum, this gravity also affects the simple pendulum, because we know that the time period of the simple pendulum depends upon the acceleration due to gravity, that is by this formula. So T is equal to 2 pi square root of L by G, where L is the length of the pendulum and G is the acceleration due to gravity. Again, in this equation, there is no mass. So you take a simple pendulum of mass 1 kg or a simple pendulum of mass 10 kgs, or you yourself hang on to a wire and go around like a swing, and the time period will be the same as long as you're falling on Earth. Now, let's talk about throwing objects under the influence of gravity. All of us know that if I throw an object, it's going to fall down initially. If I throw it horizontally, it's going to go forward and fall down onto the ground. If I throw it with a higher velocity, it's going to go farther and fall down. So what happens if I throw much farther? It's going to go much farther and fall a little farther and farther and farther. But you realize, if I throw it really fast, then it is going to fall down. But because the earth is curved, it is never going to hit the ground. It is going to keep falling, keep falling, keep falling, keep falling, and eventually it's going to hit me back with my head. So if I find this velocity such that the object has reached sufficient distance such that it's trying to fall, but the curvature of the earth is not allowing it to fall, and it's constantly falling, then that object will always try to fall, and it goes on to an orbit that is known as an orbital velocity with which I need to throw it. So an object has a centrifugal force outside when it's orbiting something, and gravity is pulling it inside. Centrifugal force is pushing it outside. So the centrifugal force formula is mv square by r, and I've got gravitational force given by gmm by r squared. Now, because an object is going around the earth, it is not going away from the earth, nor is it falling towards the earth. I know both the forces are balanced. And if I say that an object is not exactly on the earth, it is at height h, then I can change these equations such that my centrifugal force is mv square divided by capital R, which is the radius of the earth, plus height at which the object is orbiting. And my gravitational equation again becomes gmm by r plus h squared. Now, because these two forces are balanced, I can write them to be equal, and I'll get F is equal to mv squared over r plus h is equal to gmm by r plus h whole squared. So when I calculate them or simplify them, I realize I have a mass over here, I have a mass over here, so I'll cancel them. Similarly, I have r plus h on one side, I have r plus h whole squared on the other side. So one side, the whole r plus h will cancel, the other side I'll reduce the power. Because it's 2, it becomes 1. Now if I equate them, I have on one side v squared, and on the other side I have gm by r plus h squared. I have used the subscript O, so VO squared, because it's orbital velocity. And if I simplify this further, I will get for any object under the influence of gravitational force of of a planet, let's say of mass m and radius r, the orbital velocity is V is equal to square root of gm by r plus h. Now I know small g is equal to gm by r squared. So I'll take r squared on the other side, cross multiply over here. So I get gr squared is equal to gm. So this gm can be replaced by gr squared. So this becomes my equation for orbital velocity. So v is equal to square root of small g r squared is divided by r plus h. For a very small height, for example, low Earth orbit, or let's say very close, let's say some few meters above the Earth, then r plus h becomes equal to r. Okay, so r plus h becomes equal to r, almost same, like adding 1 to 1 million, almost the same. In which case r plus h becomes very small, that becomes the radius of the Earth, and then this r will cancel with this r squared over here. I will get v orbital velocity is equal to square root of gr. This is the general equation used for orbital velocity. For Earth, if I substitute the values, radius of the Earth is rounding it up to 6,400 kilometers, or 6,400 into 10 power 3 meters, and g being 9 to be 7 with a velocity of 7.92 kilometers per second, it will go around being in an orbit around the at a height of h. So that is the orbital velocity equation. And how long will it take to complete an orbit? Of course, we know velocity is equal to distance by time. So orbital velocity is equal to orbital distance by time. So orbital distance I know is 2 pi times the radius. Okay, and time, let's say the orbital time is t. So I will equate the orbital velocity to the distance traveled, which is 2 pi r plus h, which is the circumference of the orbit divided by time. And when I cross multiply, I will get, I'll just take it an inverse because I want t on the numerator. And when I simplify it, I remove the square root. I'll get t squared over here, and 2 becomes 4, pi becomes pi squared, and r plus h whole squared is equal to r plus h divided by gm. Or t squared is equal to 4 pi squared r plus h whole cube. I'm cross multiplying this term over here with this and divided by gm. Or for Earth, if I want this value, then I will find this orbital period to be 4 pi squared 6.4 into 10 power 6, which is the radius of the Earth is 6,400 kilometers, plus h whole cube divided by g, which is 6.6 into 10 power minus 11 multiplied by the mass of the Earth, 5.9 into 10 power 24. So for any object orbiting at a height h, the orbital period, the how long will it take to complete one orbit, is given by this equation. Okay, so yeah, this is the equation I have, and these are the values I've substituted. This is a general equation, so you can do this for any planet if you want. So when I substitute, uh, if I want to find or simplify this such that I want to find a height, I want to know how long something orbits, then I need to find the height. Then if I simplify the equation, I will get this when I cross multiply the denominator, and the equation becomes simpler like this. Okay, so here I've taken this term and cross multiply it with t, I get this whole term. This pi 4 pi square I've taken to the other side, so I get this. Because there's a plus sign here, I'll keep it for now, and then I'll open the cube. Okay, because there's cube over here, I'll take the cube root of this whole term. So cube root can be written as whole power 1 by 3, and then this plus term can be taken on the other side, it becomes minus. So I've got t squared plus whatever this g value is plus mass value divided by 4 pi squared. I'll take the cube root of the entire term minus 6.4 into 10 power 6 will give me h. Now, if the orbital period t is the same as the Earth's orbital period, Earth's rotational period, then what happens? Then we have an Earth-like orbit. Okay, in most textbooks they take t is equal to 24 hours, but I would like to take the proper orbital period of time, the rotational period of Earth, that is 23 hours 56 minutes and 4 seconds. So if you calculate this, this becomes 86,164 seconds. Okay, 86164 seconds I'll substitute that into this equation. T squared I'll substitute as 86164 squared, and the whole equation I'll calculate. Then I will get h to be 358 into 10 power 7 meters, or in simpler terms, my geostationary altitude, where the orbital period of the object or the satellite is same as the rotational period of the Earth, that is 35,800 kilometers. Like I told you, if I take t is equal to 24 hours, I'll get 35786. Okay, so this is the geostationary orbital altitude. The satellites that orbit with the Earth at this altitude appear stationary. So you can see this example over here. Here they've shown the satellite is above uh, somewhere over here in Chile, I think. So you can see as the Earth orbits, the satellite also orbits with the same orbital period. So it looks like that satellite is always above this country in Latin America, right? So this helps with many communication satellites and GPS satellites and so on. So this is known as a geostationary orbit. Now, let's talk about gravitational potential. What is potential? We know potential for any object is the amount of work done to bring an object from infinity towards that object under its force. So we have electrostatic potential, we've got gravitational potential. Both have a similar way of working. We calculate the work done, which is nothing but the force times the distance used to travel. So in this case, it's from infinity to a distance x. So I'll calculate dw is equal to the gravitational force. Remember, for radius, I put this distance x, okay? Just a small substitution. So dw is equal to gmm by x squared into dx. I've substituted gravitational force times dx over here, and it's dw. So to find the work done, I will integrate it from what two limits? From infinity to r. I'm bringing the object from infinity to r. Okay. Uh, so here I have gmm by x squared into dx, or gmm are constant, so I'll bring it out of the integral, and all I have is 1 by x squared, and the integration of 1 by x squared is minus 1 by x. Okay, and when I put the integration limits, I'll get minus gmm into 1 by r minus 1 by infinity. 1 by infinity is nothing but 0, so I have w is equal to minus gmm by r, or I'll call it the gravitational potential, which is minus gmm by r. This minus only says that the object is being pulled towards whatever the object of mass capital M is, and small m is the mass of the object, and r is where it is going to be pulled to. Okay, so this is known as the gravitational potential. This is basically the energy, the potential energy of any object under a gravitational field. Now, if something needs to escape the gravity of an object, let's say for Earth, then on Earth, an object moves away from Earth. When it is moving, it has a kinetic energy, and that kinetic energy is being pulled back by the gravitational potential. So if I want to escape this gravity, my kinetic energy must be greater than the potential. So to escape, of course, I have to overcome this u. So u is minus gmm by r, and my kinetic energy when I'm moving away from Earth is half mv squared. So if I equate them, I'll get gmm by r is equal to 1 by 2 mv squared. Because I'm escaping the gravity, I will put a subscript e to the velocity, which becomes my escape velocity. So mass on both sides will cancel, small m will cancel. So I have 1 by 2 v squared is equal to gm by r, or v squared is equal to 2 gm by r, or simply v is equal to root of 2 gm by r. This is known as the escape velocity of any object. If it is for Earth, I will substitute r as the radius of the Earth and m is the mass of the Earth. Or for any object of any mass m and size r, this is the escape velocity. So you need to throw an object with this velocity for it to escape the gravitational pull and go into space and not come back to Earth or any other planet. So to escape Earth's gravitational pull, let's see what is the velocity. So I'll substitute g as the gravitational constant and m as the mass of the Earth, and r as the radius of the Earth, as I've taken in the earlier case over here. So if this is the case, if these are the values, then I'll get the escape velocity to be 11,600 meters per second. It's 1,000 meters, so I'll take it as 11.6 kilometers. So for any object to move such that it escapes the Earth's gravitational pull, it has to move with a velocity against Earth's gravity, with this velocity being 11.6 kilometers per second. I hope you realize this is very, very, very fast. Similarly, for Mars, if I'm supposed to substitute, then I've taken the relative mass of Mars. So Earth's mass multiplied by this value. Similarly, Earth's radius multiplied by this value. When I substitute the value for Mars, I will get it as 5.02 kilometers per second, or 5,020 meters per second, which means on Mars, it's easier to escape the gravitational pull compared to Earth's. Okay. Similarly, on the moon, because we have seen Apollo astronauts jumping around on the moon, if we calculate this for the moon, I will substitute the mass of the moon, that is 0.7 into 10 power 24, and radius of the moon, that is 1740 into 10 power 3, then I'll get V is equal to 2.38. You see, this is very, very less compared to Earth. Earth's escape velocity is 11.6 meters per second, kilometers per second, but for moon it is 2.38 kilometers per second. Oh yeah, sorry, I've made a mistake over here. It's kilometers per second. So for moon, it is 2.38 kilometers per second, which means it's easier to escape the gravitational pull of the moon, or it means that moon does not pull you as hard as Earth. That is why the Apollo astronauts, when you see them, they are jumping around the moon and they jump very long distances and very high. This is because moon's gravitational pull is less. Similarly, for various planets, you can calculate this value. You can take a screenshot if you want for the values and calculate the escape velocities. This is what you'll find it for different planets. On Jupiter, you can see the escape velocity is 60 kilometers per second. Okay, so again, for the sun, if I want to calculate, then mass of the sun is 1.9 into 10 power 30 kgs, and the radius of the sun is so large, it is 696340. That is 6,96,340 kilometers in radius. And when you calculate this value on sun, you'll get the value high. So escaping sun's gravity is not very easy. If this escape velocity is equal to speed of light, then what happens? Because we know that speed of light is the fastest, and if you have to escape the gravitational pull such that the escape velocity itself is the speed of light, then what happens? Then I'll simply substitute V as C. I'll get C is equal to square root of 2gm by r, or I'll get C squared is equal to 2gm by r, and then I'll get r is equal to 2gm by c squared, which means if I have a mass m and I uh, compress it into this radius r such that for that mass m, the radius is equal to 2gm by c squared, then it is known as the Schwarzschild radius for that mass, and then that object becomes a black hole. For Earth, I need to compress whole of Earth's mass into a few centimeters for Earth to become a black hole. So this is the radius of a black hole, that is the Schwarzschild radius. Now, since we are talking about gravity, we all know that there's something known as the center of gravity, which is basically the point where the mass distribution of the object is said to be fixed. So if I have a large object, I can assume the entire mass of the object to be fixed in one point. Usually under a uniform gravitational field, center of mass and center of gravity are the same, but in a non-uniform gravitational field, there may be two objects pulling on the subject over here, in which case the gravitational center may be slightly off from the center of mass. Now, to balance any object, or for an object to be stationary or stable, we know that wherever it is touching the ground, or between the two or several points it's touching the ground, the center of gravity should be between those points. Like here in this case, the disk is touching the ground here, and the center of gravity is along that same point. So it will be stable. You can make a disk stand like this if it's not too thin. Or a disk can sleep easily like this because it's touching the ground in this entire surface, and COG is right here. Or this, the same thing, the center of mass is here in case of this hollow disk, and it's touching the ground under the same point, so it will be stable. If it's a bus, then the center of gravity, if it falls between the four tires, then it is stable. As long as the bus kind of leans, let's say sometimes when it's taking when there's an angle of banking, as long as the center of gravity is between the 2 points of the tires, it will be stable. The moment the center of gravity falls outside the 2 points of the tire, then it becomes unstable and it might topple off. Similarly, when we are doing yoga, most of the times we kind of lose our balance because our center of gravity is not balanced properly. When you're doing proper yoga, your center of gravity always falls between your two legs, or just falls above the one leg with which you're balancing. So center of gravity is very important when you're trying to balance stuff. Another aspect of gravity is when you're accelerating in space. When you're accelerating in a lift, for example, let's say the lift is stopped, then there's an acceleration on you downwards because of gravity, and the lift is not accelerating at all, in which case the resultant force is given by this R, such that mg plus ma, where a is the acceleration of the lift. So if the lift is stationary, then the acceleration of the lift is 0, then the weight acting on you is nothing but m into g, which is nothing but your normal weight. But if the elevator starts moving up, then the resultant acceleration that you feel, the inertia, is usually downwards. So we have mg plus ma. Both of these will add up. So this is your weight. On top of that, something extra has been added. So your weight, if it is equal to mg, it will be 2 times mg. Or if the lift accelerates less than g, then you'll find your weight increases. That is why when the lift accelerates, we will feel heaviness in our knees, as if our weight is suddenly increased. Similarly, when a lift is falling down, we take the inertial acceleration to be opposite to g. So we'll have a minus a, or mg into, or mg plus m into minus a, or mg minus ma. When you, if this a is equal to g, then I'll get mg minus mg. Then my weight becomes 0, or I'll experience weightlessness. If the a is not equal to g, then you realize this is your weight minus some value, some over here. So it feels like your weight has reduced, and you'll feel lightness in your knees. So this is something because of gravity and acceleration. We'll come back to later, but let's ask this important question now. What causes gravity? This is the problem. Newton explained how gravity works. He gave us an equation, F is equal to gma by r square. So if I change the mass, how will the gravity change? Newton told us. If I change the radius, how will gravity change? Newton told us. But what really causes gravity? Newton did not have the answer. And the answer to this was obtained when Einstein gave us the equation, and he explained gravity in terms of equivalence, and he equated gravity to be equal to an accelerated frame. Like if you're in a rocket moving with an acceleration of 9.8, and if you drop a ball, that ball will fall towards the floor of the rocket with an acceleration of 9.8, as if it is under the influence of Earth's gravity. So accelerating a frame is equivalent to gravitational force. This is what Einstein said. And when you equate this further, you will get this beautiful equation, very complex equation, which is the GTR, or the general theory of relativity equation, which tells us that gravity is nothing but a resultant of space-time. Space-time is around us, and when you keep a mass, when you keep some mass in the space-time, it bends gravity such that this slope of gravity, the potential of gravity that you have, causes things to fall towards the object. And you can see here, initially they show the Earth along this fabric of space-time, and the moon is rotating in the slope. Similar, the Earth is also rotating in the slope caused by the sun. So gravity is caused because of bending of space-time. And for all of you listening right now, you have a future in learning about gravity, because today gravity is a very hot topic, because we are studying gravitational waves. When two stars combine together, when two neutron stars orbit each other, or when two black holes merge, they create waves in the fabric of space-time. And in India, we are having LIGO India being developed right now. So we have a very big prospect of research in India related to gravity. So hoping that I've explained all the aspects of gravity, I would like to end this session. Following are the references, basic books that I've referred, which you can also refer to understand whatever I've explained here. And if you have any questions related to gravity, you can email it to me to the email ID given over there. Thank you.
Okay, thank you, sir. Hello.
Thank you, sir.
Thank you, sir. Students, any questions you ask? ಇವತ್ತಿನ ಉಪನ್ಯಾಸದ ಮೇಲೆ ಅತುಲ್ ಭಟ್ ಸರ್ ಅವರು ಕೊಟ್ಟಂತಹ ಗುರುತ್ವಾಕರ್ಷಣೆ ಈ ಶೀರ್ಷಿಕೆ ಮೇಲೆ ಯಾವ್ದಾದ್ರು ಕ್ವಶನ್ಸ್ ಕೇಳಿದ್ರೆ ಕೇಳಬಹುದು ಇವಾಗ. ಸರ್ ಯಾವ್ದೇ ಕ್ವಶನ್ಸ್ ಚಾಟ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ ಇಲ್ಲ, ಮತ್ತೆ ಇದ್ರಲ್ಲಿ ಹಾಕಿಲ್ಲ ಸರ್ ಅವರು.
ಓಕೆ.
ಸೊ ಲೇಟರ್ ಆನ್ ಐ ಸೆಂಟ್ ಥ್ರೂ ಮೇಲ್ ಸರ್.
ಓಕೆ ಸರ್. ಓಕೆ ಓಕೆ. ನಾ ಎರಡು ಕ್ವಶನ್ ನಿಮಗೆ ಕೊಟ್ಟಿದ್ದನ್ನು ಕೂಡ ಶೇರ್ ಮಾಡಿಕೊಂಡು.
ಎಸ್ ಸರ್, ಆಲ್ರೆಡಿ ಐ ಶೇರ್ ಬೋತ್ ಗ್ರೂಪ್ಸ್ ಅಂಡ್ ಚಾಟ್ ಬಾಕ್ಸ್.
ಓಕೆ ಸರ್. ಓಕೆ.
Okay, thank you, sir. Once again, it's an immense pleasure to thank you, Dr. Atul Bhat, sir. for this wonderful speech on gravitation. This talk has given many information to students. I gratefully thank you on behalf of our KSTA and personally. Thank you, sir.
Thank you, sir. Thank you, everyone.
I
Thank you for your
also
patience.
thanks our KSTA CEO, Dr. Ramesh sir, for this encouragement to organize this talent search program. I am gratefully thank you, sir.
Thank you.
And I also thanks our Chairman Professor Ayappan sir and the colleagues, technicians, and staff members for their participation to conduct this program. Once again, I thank to each and everyone. And I also thanks our all attendees and students and teachers and lecturers. Okay, sir. Thank you once again.
Thank
Thank
you.
you very
Thank you,
much.
sir. Thank you, everyone.
Thank
Thank you.
you, sir.